Hi, because we have about half of our class, a third of our class,
Stephen will be here. He's at the chapel.
40% of our class, we are going to record what we do today, and what we do today is actually fairly important. We're going to be talking about the 3 different forms that information can come to you. If you'll close the door, we'll get to it. So my plan is to talk mainly about 3 forms of information. And if we have some time, then I can take any homework questions that you might have there at the end. So on Edmodo, I have put, let's see, where are you? You are not calculus, you are physics. On Edmodo, I have put a handout for today, and if you are following along at home, you can get that, pull up that handout also. And it's called 3 forms of information. And when I pull it up, it looks like this. Let's see if I can open that. What to do? Oh, silly computer. Here we go.
I was at a cheerleading meeting.
Great. Okay. Now, what you have here is some information that is given to you about position and time, and it's given to us in 3 different forms. So our goal here is to now understand those 3 forms, how to read them, and how to convert one form to another form if it's going to be useful for problem solving. The 3 forms that we have, and it's a little bit hard to see up here, but you guys can see it on the handout if you have it on your iPad there. We have, first of all, an equation. That's our first form. EQN, short for equation. That tells us, in this case, the equation represents position versus time. And I'm going to take that equation and copy it over to here. X of t equals 1 plus 5t. And in the original handout, that's for t's between 0 and 0.6 seconds. Why don't you just look on with somebody? Okay. Now, here are the important things to observe about this. First of all, what an equation does is it gives us, in this case, position at any time that we want, as long as the time is in my domain. So pick a time that is in the domain that we're talking about. 7 seconds. Is that between 0 and 0.6? 0.5. That works. And so now I can find the position at 0.5 seconds simply by plugging in right here, and that's going to give me 3.5 meters. So notice that what we're doing here is we're essentially tracking this object, and we have captured with the equation or the model where that object is for every single time t in the domain. The second thing to observe about this is that this domain is truly limited here. After I get past 0.6 seconds, this equation no longer applies. Does that make sense to everybody?
What does the M represent?
What does the M represents units here. And very often with this equation will come some notation, something like this. T in seconds, X in meters. And so that will tell you the units that you're working with. Yes? They disappeared right before school started. Yeah, yeah. So I'm just kind of roughing it, hoping they'll show up. If they don't show up by the end of next week, I'll probably order new sets. They're not active. They're just little pieces of plastic. Yeah. So.
Did you like lock them away or something?
No, I had them like Friday the whatever before school started, and then when I came in on Monday for teacher stuff, it was gone.
Did they do like Sunday school or something?
Yeah. So maybe. I don't know.
Some 4-year-olds like
Yeah. It's not bad. I once had students deliberately steal some chemicals as a prank. Some dangerous
They
chemicals.
still like it.
Some dangerous chemicals. Well, it was sodium. It was 25 grams of sodium. I kind of left it unsecured, and they nabbed it, and left basically a ransom note.
Did you get it back?
Well, yeah, they weren't actually trying. They were trying to make a point, like, don't leave this around.
Wait, what did the ransom note say?
I don't even. This was in like 1995. I don't even know. I've become more responsible since then, but apparently not with my pens. So here it is. Now, here's how you would translate all this. Suppose I ask you this question: what is the average velocity on the interval 0 to 0.1 seconds? Okay. So now we would use our formula plug and solve method that we've talked about, and we would say average velocity is equal to delta x over delta t, and the way in which we would compute that with an equation is to compute the position at each of these times and subtract. And x of 0.1 is found by plugging in right here. Everybody, what is x of 0.1? Do it in your head. Ah,
I'm sorry. Wait.
Yeah.
You're fine. I was right.
it's okay. What is x of 0.1? He knows. How did you find out? Ah, what is x of t for a t? Yes. See, that is the point I wanted to get across, is that this thing really does give you the position at any time you want. And if the time you want is 0.1, 1 plus 5 times 0.1 is 1.5. All right, how about x of 0? It is 1.
Yay.
And all of this is going to be in meters because x is measured in meters. That's the middle school number. Meanwhile, down here on the bottom, this is going to be measured in seconds because t is in seconds. And when the dust settles, I get 0.5 over 0.1, which is 5 meters per second.
Wait, how did you get 5 meters per second?
I did the arithmetic. 1.5 minus 1
Oh, 0.5.
divided by 0.1.
Oh, that's a point. I thought, yeah, that was
And since I'm computing a velocity, I'm going to remember to put a plus sign in front of my positive numbers because velocity has direction to it. So that's my final cleanup that I need to do. Yes?
Can you kind of explain what you did in x of 0.1 minus x of 0?
Well, sure. Average velocity is the displacement over the time, or the change in x over the change in time. So we're looking here at the final position minus the initial position. That's displacement.
So then how did you end up with 1.5?
What is x of 0.1? What is x of t?
Oh,
So what is x of 0.1? You know, it's funny, you spend 2 years in algebra working with these equations, and it's not until you come to physics that the light bulb goes on and you go, oh, that's how we use this. And now that you've seen it, it will never be a mystery again. Yeah. Angela, doing good? Okay. I wasn't sure from your expression. All right. So this is how we use equations then. We use them, here it is, by plugging in, by substitution, essentially. Okay? Now, what if this same information was given to me in graphical form? So back to our, oh, really?
I don't read it.
Rate it a 1. It's in our figure. Class guys.
I am not going to, no.
Read it.
Rate it.
No.
What?
Why?
Install the oh, that's what they're doing. They're selling me up. Oh, that's funny. No, not good marketing. Short-sighted marketing. All right. So this is the second way in which information can come to us, and that is in a data table. I want to be clear that this data table is trying to express the same thing that the equation is doing, but it is giving me specific selected values. Now, they are not exactly the same. The specific selected values are probably measurements of some sort. And I take those measurements, and through super secret mystical statistical arts that I will share with you in the future, we can turn those into a model such as our equation 1 plus 5t here. So they're not exactly the same. This guy is trying to be a more complete version of the data that I actually collected here. This probably comes from hard measurements. This comes from some math analysis. Does that make sense? Okay. But that said, they're trying to say the same thing. And look at that. Look at what x of 0.1 is. 1.5. Exactly as we predicted. Look at what x of 0 is. 1. Exactly as we predicted. So the way that I would use a data table for a similar kind of question would be like this. If I have the data in the table, and I ask what is V average on the interval, make up an interval for me in domain. It has to be in domain. What's the domain of our...
0.
Okay. 0 to 0.4. What is the V average on this guy right here? Then I would respond by giving my formula. V average is, everybody?
Displacement over time.
Displacement over time, so delta
X
X
over
over
delta
delta
T.
T. And if you forget, think about units. Meters per second. It has to be X over T. Yeah. Okay? But now to get the delta X over delta T, I am going to read the numbers directly off the chart and go to 0.4 and read that X, which is 3. And go to 0 and read that X, which is 1, and plug them directly in. And when I do the arithmetic there, lo and behold, again, I get 5 meters per second. So I'm using the same formula, but because my information comes in a different form, I evaluate that formula in a slightly different manner. Does that make sense? In other words, the concept is the same. Average velocity is still delta x over delta t. The difference in the form of information makes the execution of that concept slightly different. That's all. That's really the point of today's lesson. Okay? How are we doing? Okay, good. Now, the third form of information that you have is a graph. And what the graph is going to do is take these same data points that we had right here and it's going to try to draw a smooth curve through those data points. The word curve in astrophysics means any continuous graph, so it doesn't have to be curvy to be a curve. A straight line is also a curve in that. That's just a thing. So the key here is you notice that my graph also fills in the points in between my measured data points. So it's doing something very similar to the equation, and that is that it's trying to capture the behavior for the entire interval 0 to 0.6, not just at the points that I happen to sample. Nevertheless, it's trying to give me the same kind of information, which is the position versus the time. So, if I were trying to do average velocity on an interval, let's see here. Yeah, give me an interval that is somewhere in the domain 0 to 0.6. Great. So let's ask the question from the graph, what is the average on the interval 0.1 to 0.5? Then I would begin in exactly the same way that I've begun for all the others. What is the average? The average equals, which is written
Change in x over change in z.
to x over delta t. And notice that after I've written that formula 3 times, I'm pretty comfortable with it, right? And it seems not so scary anymore. Hence formula, then plug in, then solve. It's a super secret way of actually learning things. And now, to get my delta x and my delta t, I am going to go to the graph and read the data points off at the appropriate time intervals. Going to 0.5, which is my final point, it looks like my position is right around 3.5, but I have to read that off the graph. So you might get 3.4, 3.6 if you read it off the graph, right? I'll call it 3.5. Minus, going back to the graph, at point 1, looks like my position is 1.5. Over 0.5 minus 0.1. This is in meters, this is in seconds. How did I know that? On a graph, the units will always, this graph failed. This is supposed to have x in meters and time in seconds. Bad
Oh,
graph.
yeah, it's on the bottom and x in meters.
Oh, I drew over it. Okay, my graph didn't fail.
See what you.
All right, there we go. I apologize, graph. It was not your fault. Please give me the information. So, the units right there become the units that I put into my computation right here. There's never a mystery about it. Does that make sense? And so then we get 3.5 minus 1.5 is 2. And 0.5 minus 0.1 is, and 2 divided by 0.4 is 5. It's the same as 20 over 4.
Oh, yeah.
And what's the one thing that I'm missing here?
The
The
plus
sign,
sign.
the plus sign, which indicates a positive direction. She gets it. Good.
Okay.
Go ahead.
For the table, sorry, I'm going back to the data table.
Yes.
Do we have a plus with that side?
We should, and we do.
I can do that, right?
We should and we do. Yep. It's a little hard to discipline yourself to do 2 things. One is to have plus or minus signs, and the other is to have the units. And you want to, just over time, I'm going to fuss at you, and you'll eventually do it, so you don't have to fuss at you. So that's how we use the 3 forms of information. And at this point, how many of you can identify with Angela? You say, oh, I get it.
I can.
Awesome.
We have to like do it for an assignment to actually
see if I get it or not.
Okay,
Like a
well,
whole
let's see if you actually get it or not. Let's go to the next page.
My bad, guys.
Oh, no. Can we not go to the next page?
Oh. Okay, on the next page, we have for ourselves table of values, equation, and graph. Here's what I'd like for you to do. I'm going to ask some questions, and I'm going to have you evaluate those questions based upon one of the three forms of information. Okay? So, not like that. Find the average, and here comes some different time intervals. Interval, first of all, 0 to 0.2. And then, on the interval 0 to 0.15. Go ahead and grab a partner that you can work with, and I'd like for you to answer these two questions from the information that's found there. If you need that information, you can see it right here. See if I can get this any bigger. Oh, that's much better.
Oh, boy. There is no 0. We can see 0 was 0.1. Has to be somewhere
Oh, wait a minute, I didn't even finish this one. Yeah, you know what, sweet. Yeah. I was like, oh, here's the difference. It's easier to make.
No, I'm not gonna tell you.
Yeah, we're
Did you subtract the 4.9? It's 2 squared, right? 4.9.
Yeah, sure.
4.9 T squared. Okay. Because I'm gonna try to do this again, see if I get a different answer.
2, 6.
Oh, okay. I did like order number.
Nailed it.
I have to start it over.
I always say, oh.
There we go.
I
That's
understand.
It sounds logical. It sounds logical. It's that 0.15 thing that. But I think I got it. Got it.
So who has the answer for the first one?
oh gosh.
Raise your hand if your group has an answer for the first one. Okay. You good? How about for the second one? Working. Okay.
Excellent.
These
Hold on.
These are intervals, right?
Yeah, I got that, but then you have to divide it by. There we go. Okay, we got the answer. Okay, good. So 4.
Okay. Which form of information did you guys use for the first one, 0 to 0.2? You used the equation, okay? Which form of information did you guys use? The equations. Which one did you guys use? The data table. Which one did you guys use? The table, equation, and Hannah? Equation. So about split, 50-50 on the equation and on the data table. I'm going to show how using the data table would work, because that, to my mind, is the easiest way to go, because I have our data for both of those points. So we start with V average equals, everybody?
delta X over delta.
Delta T, and after the fourth time that we've done it, we're really good at that formula. So I now plug in 4.104 minus 4 meters per second. Oh, that's interesting. This x of t is in meters per second. What is that? No, this really should be meters. That doesn't make any sense. This has to be meters. Yeah, that was kind of dumb. I need to go back and fix that. Here we go. And now we get meters per second here. We get 0.104 over 0.2, which is the same as 1.04 divided by 2, which is going to be positive, positive 0.52, but I have to round to 1 sig fig because I only have 1 significant figure in the bottom. So I'm going to get positive 0.5 meters per second.
How did you get minus 4 meters on the top? Where did that come from?
So remember that delta x is final minus initial?
Right.
And so my final was here, and my initial was here.
Oh, okay.
Yeah.
Oh, it makes so much more sense because those are the 2 points that
Those
we
are your
started with.
That's right.
Okay.
That's exactly right. If you did it by the equation, hopefully you have the exact same numbers.
I got some, but then why didn't you get to the
Well, 0.104 divided by 2 is the same as 1.04 divided by 2.
We got,
So then when you divide, you get 0.52.
how would we?
And then you
I
round.
need a minute to process. Yeah, I'm struggling. Thank you.
Because when we did the equation, we solved for the
I solve for x, and we got 4.104, which is what's up there.
Sure.
Then how do we get to the next part?
Average velocity.
The
Yeah,
average velocity, like how do we?
that's the question I was looking
Well,
at.
actually, you start with average velocity as this. Did you write that?
Yes.
Okay. And then delta means final minus initial. So you actually have two x's, right?
Yes.
You have x at the final, and then minus x initial, which is from the zero. That's exactly right. Okay.
Actually, teacher, do you know?
Yep.
You rounded to one sig fig because of
The bottom right there.
0.2.
Yeah. Yep. Okay. Good. Now, what about the v average on the time interval? Can I erase all this? What about the v average on the time interval 0 to 0.15? At this point, one of the three forms of information is not going to be useful to me. Which one? The table, because I don't have a data point, I don't have a position for 0.15. So I'm going to have to use either the equation or the graph. How many of you guys use the equation? How many of you use the graph? Okay. I'm going to use the graph just because it's not what most of you did, but hopefully the numbers will come out very similar. If I go to the point 0.15, that's this point right here on the graph, looking at these points, 3.9 to 4.2 is a distance of 0.3. But in my mind, I go roughly in thirds. 0.1 is 4, 0.1 is 41, 4.2. Looks like we're looking at 4.1 right here for my final position. Minus initial is 4 all over 0.15 minus 0 meters per second. You guys that did the equation, you probably didn't get exactly 4.1. You got something close to that, which was what? 4.115. So when you get an answer, your answer is going to be a little different from mine, but then watch what happens when we round.
Okay.
So I get 0.1 over 0.15, which turns out to be, oh, I don't know.
We got 0.6.
Yeah. Right, it would be 2/3, of course. And it's positive 0.67, which rounds to positive 0.7, 1 sig fig, meters per second. And my guess is if you did the equation, you got something that rounds to positive 0.7 meters per second. All right? So one of the things, this was a question I think that you asked me about your homework, one of the things that happens is when you get an answer, your answer and the book answer may differ by 1 in the last place because of rounding issues. Yeah.
Where do you have a negative answer?
When do you have a negative? That's a great question. If I take a look at the graph here, what this number represents is the slope of the line that connects these 2 points. It's hard to
There's
see.
just the 2 points. Okay.
Yeah, right. So if I were to go here, then that line connecting the 2 points would be like so. It would have a negative slope. We have a negative average velocity. Meaning that from here to here, my object goes backwards.
Okay.
Yes, sir.
Can you still use the equation? Because it shows how you.
Oh, yeah, sure. Yeah, that'd be fine. If I use the equation, 90 squared plus 1.5t plus 4. Oh, I just reordered the terms. And so then, if I were to do v average, I would again do delta x over delta t. And that would be x of 0.15 minus x of 0 all over 0.15 minus 0. And then I would plug in 0.15 into the equation. And when I do, what value did you get for your x? Of 0.15.
For the delta?
No, just for the x.
Just for this. I got 4.114.
That has way more sig figs than I deserve, but I'm not going to worry about that until the end. Okay. And then, when I subtract, notice that because of having two significant digits here, I actually get a little more precision with the equation, which is fine. And in particular, I get plus 0.77 meters per second. And there it is. Does that help? So, hopefully you see how all these things work together. The last question we have, and I think I have about 5 minutes to answer it, is how do I go back and forth between those forms? One of the most important problem-solving skills that you can have is to know how and when to change forms on your information. Probably some of you are going to be skilled at some of these. So if I, for example, have data and I need to go to a graph, well, that's pretty easy. How do I take data and turn it into a graph? Plot the points, that's right. And then you draw a smooth curve between them. Or you draw a best fit line. Have you guys done best fit lines in chemistry? You know what I'm talking about? Did them in algebra 2. Okay. We're going to do it again for your labs. The reason you do them in algebra 1 and 2 is so that you can actually do them in a scientific context. So one of the most common things that people do is they will take numeric data like this, and they will say, well, let's pretend that these data lie on a straight line. What is that line? Let's draw it. Boom. And that's the best fit line. And that now turns into a simple equation because all lines have what form? Ta-da! That's it. And we love that, and we're really good at y equals mx plus b, so we're playing to our strengths. So data can go to a graph. Graph can go to a data table if I need to. I just read points off of the graph. That's easy. Likewise, I can take an equation and turn that into a graph simply by graphing it. Or if I need to, I can turn an equation into a data table by picking the appropriate values of x and finding the corresponding values of y, or in our case, t and x. Right? What's the hard part? The hard part is taking a graph and turning it into an equation, or taking data and turning it into an equation. In some big sense, all of physics is a search for how to turn the data that you have collected into the right equation that models those data. In some sense, that's 350, 400 years worth of physics in a nutshell. I've got all this experimental data. Now, how do I find the right equation for this? So we are going to answer that question slowly in pieces as we progress through the course. But let me give you the short answer right now. To go from a graph to an equation or from data to an equation, I'm basically going to draw two things. First of all, I'm going to draw on simple models. Y equals mx plus b is a great start. Or if my data are curved, how about a quadratic, right? So I'm going to go for simple models, and I'm also going to rely on statistics so that I can take a bunch of data points that aren't perfectly on a line, but they're pretty close, so that I can take those data points and say, on average, they fit on this line. I'm not going to teach you everything there is to say about this. If you're an expert in this, you can you can earn a salary of about $100,000 a year doing what they call modeling, not modeling, but modeling. And that means taking data and turning it into equations. Big demand for that kind of thing at this time right now. So I won't tell you everything because I don't know everything because there's not enough time, but I will tell you a little bit about how to do that. Yeah.
What do they do in modeling?
You're taking a bunch of data and you're saying, what is the equation that predicts these data? That's right. So wouldn't it be nice if I could come up with an equation that would predict the stock market in 2 months? Boom, lots of money. Wouldn't it be nice if I could come up with an equation that predicts who's going to win the election? Wouldn't it be nice to know what's going to happen? Wow. Oh my goodness. Wow. Maybe I better turn the recording off. So anyway, the changing forms, the stuff in black you pretty much know how to do, right? The stuff in red, we're going to be learning how to do as we move through this course. Okay? Good. Good work, I think.
Do your homework now?
Yes, take your homework, and let me turn off the
Can I
recording.
give you my class?